Howdy, this is Jim Rutt, and this is The Jim Rutt Show. This is a Currents episode. Currents are shorter and less heavily produced than our full-length episodes and generally focus on a single topic. As always, links to books, articles, and organizations mentioned are available on the episode page at jimruttshow.com. That's jimruttshow.com. Today's guest is Chris Conselice, professor of astrophysics at the University of Nottingham in the UK.
Hi, Jim. Great to be here.
Really good to have you here. We're going to talk about something that listeners to this show know that I'm very interested in, which is there intelligent life in the universe? Actually, in this case, we're going to be talking about, is there communicating extraterrestrial intelligence? Chris and his co-author, I don't have your co-author's name in front of me. Why don't you tell me your co-author's name?
The co-author was Tom Westby, and he is the first author, and he's the one who took really the lead in writing the paper and doing the analysis. I was more of his supervisor. He's a master student who works in engineering at the University of Nottingham and in mathematics. He's like a kind of like a lecturer type position there, where he does quite a bit of teaching. And he was interested in doing a project in astronomy with me, and this project on asking about how many communicating intelligent civilizations there are is not really something that, let's call it, mainstream astronomy would sometimes approve of or do. And so someone who wanted to do like a terminal degree that's a master's would be the best person to do this kind of project, because he's not interested in having a full-time career as an astronomer. And I'm already established, so they can't get rid of me so easily.
I love it. It's kind of like in cognitive science. Speculation about consciousness has that same attribute. You better wait till you get your Nobel Prize, or at least till you're a tenured professor, to ever to say the C word, or you'll be in big trouble. Right? Fortunately, that's starting to break down. I hope SETI becomes a more legitimate field. I mean, we had Jill Tarter on the show back in September, and of course, she spent her whole life fighting against the prejudice against both female astronomers. And SETI, and has done lots of very interesting work.
Absolutely.
Anyway, the paper we're going to talk about today was recently published by Chris and his co-author. It's called The Astrobiological Copernican Weak and Strong Limits for Intelligent Life. It's published in the Astrophysical Journal. But for most of us, getting it off the archive server is just fine, a pre-press version. A little ugly, but it's definitely readable. And as always, we'll post a link to that article on the episode page at jimruttshow.com. Again, as listeners to the show know, I am absolutely fascinated with this question about extraterrestrial life. In fact, my own personal hierarchy of scientific questions, I rank it number 2. People say, well, what's your number 1? And my number 1 is, why is there something and not nothing? You know, why does the universe even exist? Like SETI, that's considered a somewhat out of bounds question in some of the more established fields of science, but that's all right. But number 2 is, are we alone? Has so many huge implications about, what is the purpose of humans on Earth? What is our destiny? What's the destiny of the universe? Just gigantic question. And this is a question people have been speculating about for a long time. And Chris and team have done something which is very interesting, which is they've taken the old Drake equation and they've updated it with a lot of the new findings in science, which we're going to go over here a little bit. And they've used an interesting, I'll argue with them a little bit about the appropriateness of it, but this weak and strong Copernican principle, and it yields some specific numbers on how many, what's the range of the number of communicating civilizations within our galaxy. So with that, I'm going to turn it over to Chris to maybe frame a little bit about the history of the Drake equation, and some of the insights on new scientific discoveries that have allowed you to restate it in a different and perhaps more tractable fashion.
Sure. Thanks very much. Right. So essentially, the way to look at this problem is really to, in some ways, take it from a historical perspective. So for many thousands of years, people have wondered about life on other planets and other places within our galaxy and within the universe. And they've actively speculated on this for as long as really we've been able to write. So we know ancient Greeks thought about this, and we know that throughout time since then that it's also been a major question. People were burned at the stake for suggesting it, and it's been highly controversial throughout time, and simply because we just don't know, and we still don't know. We don't have an answer, and my paper doesn't tell us an answer either. It just gives us some benchmark for how to measure this question and what the potential answer might be within a few assumptions. So with that, for let's say a couple 100 years or so in the past from now, the astronomers that thought about this question were quite bullish on the idea that there is life throughout even the solar system. So, for example, astronomers like William Herschel and his son John Herschel, two of the most distinguished astronomers at the turn of the 19th century, both believed that many of the planets and even the sun and the moon were inhabited, that there was life throughout our solar system. And in fact, of course, you have Percival Lowell and the canals on Mars, which was a huge topic at the turn of the 20th century, with many, many astronomers believing this. Of course, there were doubts in that time. But throughout the 20th century, as we've learned more and more about the solar system, we have realized that life, at least intelligent life, certainly doesn't really or cannot exist, let's say, within our solar system, that we are really the only intelligent species within our solar system. It would be hard to believe that they could be so well hidden that we wouldn't have seen anything by now. And that, of course, happened when you had these space probes going to Mars, landing on Mars, Venus, and so on. And we know that there's no, civilizations living on Mars building canals. That's certainly not true. And there isn't even evidence for any kind of past life on Mars that's convincing, I would think, so far.
I'm going to jump in just with one little pushback, which is, there is some thinking that there could be life, maybe even intelligent life, though probably not communicating. At least, well, I don't know about that. On some of the couple of the icy moons, Europa, and what's the other one around Saturn? I forget the name, but anyway, there's two of them that's thought that will have water oceans well under the surface that could be liquid water, and will have rocky bottoms, so they'll provide the metallic ions that are necessary for our kind of life. So yeah, we could have something like octopuses or something like that down there, and who knows how far what they might have been able to develop. So I wouldn't quite rule it out in the solar system yet. And it is, to my mind, one of the very key questions that will actually help get some traction on the part of the Drake equation that you more or less punted on, which is life, does it happen all the time? Does it happen never? Almost never? Fairly often, but a random roll of dice. And looking at those undersea environments may provide us a big clue on that. But anyway, continue. Sorry for the interruption.
No. Please interrupt much as you like. So what you said is true. What I perhaps should have said in a clearer way is that there isn't an intelligent communicating life within the solar system, that we would have detected that, unless the way they communicate is very different from the way that we do. And that's hard to imagine how that might be. So what I mean by that is there's not like these octopi are not, they don't have like underwater cities that emit light or have radio waves or something, because we would have detected that by now. So that's what I really meant by that. So you're absolutely right that these moons could indeed have some form of life in them. And I certainly would not want to discourage people from thinking about that, considering that, and searching for it and having missions to go look for it. I think all that's very good and should be done. But I do think that it would be hard to imagine that there would be intelligent communicating life on those moons. But hey, if I'm wrong, that would be fantastic, right? That'd be great. Okay, so that's really the kind of the history up into the 20th century for this idea of looking for, let's say, life on other parts of the universe. And it's always been something which has been solar system focused. People really want to know about it in the solar system. People want to know and find out life in the solar system. It's really been the focus for a very long time. And personally, I think that when we noticed that life wasn't super common, at least in the solar system, that people got very discouraged about this idea of there being any kind of life throughout the universe, simply because we weren't finding it in places where we once thought it might exist. Of course, SETI happened at about the same time, and SETI is a little bit different from looking for life in the solar system, because the traditional SETI looks for radio waves coming from other stars which may be produced by an intelligence, something which cannot be produced by a known astrophysical object or a process which emits light in a way that we understand. You'd have to find a signal which looks artificial, that is, looks made by it's made by an intelligence. And that started in around 1960, and since then these SETI surveys have gotten more sophisticated and bigger, and you have various big projects going on now to look for SETI in this way, and that's fantastic. So the question that we wanted to answer, and this is something that I've been thinking about for a long time, for almost 10 years now, is can we actually say something about the number of likely communicating intelligent civilizations that are in the galaxy that we could detect right now? So there's a lot to pick apart with that statement. So you have to have life. That's the first thing. And then you have to also have intelligent life. That's the second thing. But then you also have to have communicating intelligent life. So you have to have all three of those for this calculation to work. Okay. So if you have intelligent life, so we've had intelligent life on Earth for a very long time, for maybe 100,000 years or so, maybe more than that. And we've had communicating intelligent life for only about 100 years. That's how long we on Earth as humans have been artificially producing signals from the Earth which go out into space. Okay, and you can think of this as radar, as radio waves from radio, from television, from satellites, or even lights that come from cities. So those are artificial reproductions of artificial light, which is not produced by an astrophysical process. It's produced by an intelligence, a communicating intelligence. So that's what we mean by that. And so we know that's existed on Earth for about 100 years. Okay. Now, the other thing which happened in the last decade is that we've learned a lot about galaxies, about star formation, about planets, where we can start really answering this question of how many of these type of communicating extraterrestrial civilizations might there be throughout our galaxy. And the way we approached this problem was very simple. We just said, let's assume that life, intelligent life, and even a communicating intelligent life is a natural process which happens in science. Now, this is a big question, of course. And, we could very well be wrong. I completely admit this. But we have no idea if it's right or wrong. So I would argue it's important to make that assumption and to look at what you find. So the question is, how many of these exist throughout our galaxy? How many of these communicating extraterrestrial civilizations are there? So let's just assume that they just form as a natural part of science. For example, if you have the right amount of gas at the right temperature and density, you form a star, you form a galaxy, you form different things that you see in science are produced in a way which is predictable based on the initial conditions of how you start. So why should life be any different than that? So this is really the way that I like to think about it. And this is the assumption that we make in this calculation. And we'll come back to this again about testing that assumption when SETI actually succeeds and, let's say, maps the galaxy in terms of its intelligent life within it. Okay, so what do you need to know to do this calculation? You need to know how many stars are as old as the sun. You need to know how many of those stars can survive that long. So the sun is about 5 billion years old. How many other stars that are existing in our galaxy today are at least that old? And it's actually a pretty high fraction. It's in the 90s, the percentage of stars that are in our galaxy today are potentially able to host life in terms of its age. So that doesn't really disqualify very many stars. Then you have the idea of how many of these stars have planets. And this is something which has always been a big unknown, and you mentioned this already, the Drake equation, is how many stars have planets. And this is something that we actually have some idea about now from the Kepler mission, which is a satellite mission which observed a patch of sky to look for planets around stars, and was able to say there's about 17-18% of stars have planets in the habitable zone. And the habitable zone is that area around the star which is not too hot, which is not too cold, which is able, in principle, to form life as we know it on Earth. That is the same temperature as roughly the sun at the surface of the Earth. So with those two things, you now know how many stars there are. You know how many planets there are around each sun. But at the same time, another feature, which was never part of the original Drake equation, is answering the question, well, how does the metallicity of the stars change throughout the galaxy? So the metallicity is really critical for this, I think. And the reason is, well, first of all, let me explain what metallicity is. So metallicity to an astronomer is any element which is heavier than helium. So that kind of is sometimes funny to people. When I teach this in my classes and I tell students this, they sometimes laugh because it sounds ridiculous. And I think it did to me once too, but this is the way astronomers talk. So metals are anything heavier than helium in the periodic table. So elements like carbon, oxygen, nitrogen, the big ones you need for life are all what astronomers call metals. And these all sort of correlate together. That is, when you find a star that has a lot of carbon, you also find a lot of oxygen and nitrogen and so on. They go together because they're formed in nucleosynthesis in stars, which then go supernova and go through stellar evolution, which then reproduces these elements into the interstellar medium, which is then used for further star formation. So they correlate together. So what you need, essentially, getting to the point of this, is that you need a star that has a high metal content, that is, has lots of these elements to form life, because you can't make life, as far as we know it, out of just hydrogen and helium. It doesn't exist, and it's hard to imagine how that could ever happen. If you want things like amino acids, these kind of things, you need to have these elements that are heavier than helium. So the places in our galaxy where you have these heavier elements are more likely to form life. And that is also something that has only been known in the last 5 years or so. And so we know how many stars have the right metal content. And by the way, the sun, our own star, is pretty metal rich compared to most stars in our galaxy. It is much richer than most nearby stars, at least in our own galaxy. And that may or may not have anything to do with the fact that we exist at all. But I think it does. I think you need to have these heavy elements, and you need to have them in great abundance to actually produce life. Okay, so putting all that together, you can then ask, well, how many of these stars have a planet which can host life, potentially in the habitable zone? How many of them have the right metal content? And when you do that, what you need to then calculate is how long you think these intelligent communicating civilizations will last. And this is really one of the key aspects of this, and one of the funnest parts of it. And hopefully we can get into this in more detail. But essentially, it's how long do you think these civilizations will last? This has always been one of the big unknowns within the Drake equation. And the simple thing that we did was one of the things we did was to just assume that the life which exists, which is communicating, is similar to our own. And we know that we've been around for 100 years sending out signals into space. So we just asked the question, well, what if these other civilizations only last 100 years? And we know that we've lasted 100. We may go longer. We may go, well, hopefully go longer. But, we may go 200 years, a million years. We don't know. But we know we've done 100. So let's just see, if we use 100 as the typical average lifespan of an intelligent communicating civilization, how many would you expect to find? So when we put all that together, what we find is that you have, on average, about 36. And then if you look at the error range in that, which is important, based on the errors on these values, you find that the error goes from a couple to up to about 200. So that's really the range of what you would expect based on this assumption about how life forms within our galaxy. If you think life forms in our galaxy around other stars in a similar way as it does on our own, that is, that life and intelligent life is not outside of the, let's say, scientific process of forming structure and how science works, then this is really how many you would expect to see based on a lifespan which is similar to our own at the current age. Now, if you want to believe that the lifespan of an average civilization is much longer than 100 years, then you can easily use our formula and calculate how many you would expect, and that number would go up. But this is sort of a lower limit, if you will, based on this assumption.
Okay. Let me ask a couple of clarifying questions.
Yeah.
One, in your paper, you lay out two different models, the weak and the strong Copernican principle. As I recall from the paper, 36 is for the strong Copernican principle. Is that correct?
Yes.
And if you could maybe make the distinction between the strong and the weak and provide people what the number might be for the weak principle.
Yeah, right. That's a great question. So the strong principle is that life forms exactly the same way as it has on Earth. So that just means that essentially that life will form around 5 billion years, and the error bar that we put on that is about a billion years. So we allow life to form between 4.5 and 5.5 billion years. That's when that intelligent life and communicating intelligent life will appear, is within that limited range of time. The weak principle is that it takes 5 billion years at least to form a communicating intelligent life. So that life can form at 5 billion years, 6 billion years, 7 billion years, all the way up to the age of the star, because obviously you can't have life forming in a star over a time period which is older than the star's age. So the star's age is like upper limit to how long that life can form. So that gives you a lot more time for the life to form within the star. And when you use that, you find that there's a couple thousand possible of these communicating extraterrestrial intelligence throughout our galaxy, which we call SETI with the C. That's what we call them. And so it's slightly different. So depending on how you assume things will form, that's what you would find if you only use this 5 billion years or so as a lower limit for the amount of time it takes for this communicating intelligent civilization to form.
Gotcha. And just for the audience's sake, the median age of stars in the galaxy is what, about 10 billion years, as I recall?
It's in our paper. I know I'm going to say it wrong, unfortunately, but I think it's around 9. Would be my recollection.
Actually, you have the median age as 10.35. How about that?
10.35. Okay, sorry. So I was a little bit off. So it's about 5 gig years.
Yeah. The mean age is a bit lower than that, though. We know that there's that skew down at the low end for the giant stars.
Yeah. Right.
So the median's about 10. Let's call it 10. Close enough. Another question I had that you didn't address is that I recall from the course in stellar evolution, or actually it was part of an astronomy course I took when I was in college, that the supernovas were much more common in the earlier days than today. Would that in any way change your analysis?
No, we didn't consider that. And the reason we didn't is because supernovas certainly are more common when you have more star formation events. And those will have occurred, let's say, billions of years ago. So the star formation in our galaxy peaked about 3 or 4 billion years after the Big Bang. And now we are almost 14 billion years after the Big Bang. So that was a long time ago when the peak of star formation occurred. And those supernovae would have happened within a couple 100 million years of this, when the star formation happens. So most supernova in our galaxy would have occurred much earlier in its history. And you have to be pretty close to a supernova for it to really affect the life on the planet. So it's probably not a major production or destruction of these life forms within our galaxy, especially when we know the rate is about, I'm going to say it wrong, but the rate is, I think, only maybe a couple a century at most for these supernovae happening within our own galaxy. And they're not necessarily the type which come about in star formation, but are the type 1 supernova, which are thought to be produced by gas and falling onto like a neutron star or black hole. And those are also pretty rich in energy, but again, they're not really that common throughout our galaxy's history today, at least. And so, if you have a civilization that typically can last a couple 100 years, but you have these supernovae happening maybe a few a century at most, it's very unlikely that they're going to be so close that they would totally destroy that civilization.
Gotcha. I was thinking of more as a source of metals, right? And I think our sun is thought to be at least a third generation star, maybe more, and unusually late, and that there was a supernova not that long before the sun formed that seeded it with an unusual, maybe an unusual rich assortment of higher atomic weight elements.
Well, that's a really good question, is how many supernova produce the elements that we use on Earth that made up our solar system. And that's kind of a tricky thing to know. It's probably not just one. In fact, I'm pretty sure it's not just one. It probably is a collection of many over, eons of time happening, right? So the sun formed in our own galaxy about 8 billion years after the galaxy was born. So you've had 8 billion years of evolution and and star formation and the supernova happening, which can produce tons of these kind of metals, which the solar system formed from. So it's not just one supernova, but it's likely to be very many. Yeah.
Got it. All right. Well, let's talk about this key number L, which is, again, one, why I think it's so interesting to tell us about ourselves and our destiny. L being the average length of a communicating, intelligent civilization, or let's at least call it species. It may not have a civilization, but let's call it a species that is able to broadcast, at least for these purposes, radio waves out into space. And one thing that's important to note is that if we use radio waves as the metric, there's two ways that radio waves could stop being emitted. One is the civilization loses the capacity, let's say it collapses, either from a natural cause like an asteroid or an endogenous cause like a nuclear war, or, and this is one in the study of the Fermi paradox comes up quite a bit, is maybe they stop using radio waves and they use something else. They use gravity waves or neutrino beams or even directed laser beams, some other form of communications that at least today we would have it difficult to track. Though I do know from conversations with people in the SETI world, they are now starting to think about how to detect point-to-point laser communication.
Yeah, I mean, there's a lot to say about L, right? That's really one of the key things, and you're absolutely right to say that it tells us about ourselves. So, one day when SETI actually studies the entire galaxy, and it won't be anytime soon, but let's say they know for sure that there's no life within our galaxy at all that's existing right now that we can detect. Now, let's assume that they also have rolled out these things about neutrinos and gravitational waves and stuff, and that we know for sure that there's no other life in the galaxy. Well, that would tell us a couple of things. It would tell us that either the lifespan of the civilizations on average is very short, or it would tell us that we are indeed very unique in the terms of our formation, and that our formation is sort of outside of a natural progression of science, but is more of a random thing which happened in some random way, right? Maybe life is just something which you just so happens, right? It doesn't happen by nature, so to speak, but just develops sort of on its own, in its own way, in a way that we don't really understand. So the other thing is that if, let's say, SETI succeeds and we start finding lots of these civilizations, let's say close to us. So with this 36 number I talked about, the typical distance to those civilizations will be about 17,000 light years away, which is really far, and it'd be really hard to detect a signal coming from any of those kind of civilizations, simply because of the distance, and the signal would be very weak by the time it got to us. But let's say you have detected with SETI many civilizations throughout our galaxy. Let's say within our own local universe, where if SETI exists in great abundance, that's where you'd find it first, because simply that's just the easiest to find. Then they would really tell us something about L. It would tell us that L must be quite long, that the average lifespan of an intelligent communicating civilization in our galaxy, the lifetime of that is quite long, and that would be really good news for our own existence, assuming that these creatures are similar to us in the way that we have technology, and the way that we can destroy ourselves, and the way that we can be destroyed, as you say, by asteroids or by other parts of astronomy, let's say supernova, gamma ray burst, etc. So that would really be something great for us to learn, not just that existence of life that exists throughout the galaxy and other places, but also that actually we may have a chance of figuring out how to survive on our own planet for a very long time to come. And that, I think, would be a great thing to know as well. So it tells us not only about where we came from, but it tells us where we're going and how long we might actually be around. So SETI is important for both of those things. It's really important to tell us if we're alone, but also it tells us something about where we might be going into the future and where we actually did come from. So it's really answering really fundamental questions. But I'd like to come back to this idea of gravitational wave and neutrino physics and stuff being used as sort of a more difficult way of transmitting. I find it hard to believe that if a civilization arose throughout the galaxy and was intelligent and was able to develop technology, that they wouldn't have some kind of phase where they actually were using similar technology that we do, like electromagnetic radiation, which is super common throughout the whole universe, and it's an easy way to communicate, easy way to transmit information, etc. And it'd be very hard to imagine that a civilization would go from being, non-technological to having, gravitational wave communication. That would be almost impossible to believe. So there must be some phase where they're actually doing some kind of electromagnetic transmission, and it's be impossible to have that not escape from its host planet out into space. So looking for that kind of thing, I think, is still a very valuable thing to continue to do. Now, one of the criticisms I have with SETI is I don't think that these intelligent communicating civilizations will actually necessarily want to be found, and I don't think they're sending out huge radio signals to be found. It's something that we would have to detect just based on whatever they're sending out to each other, and we just happen to catch a glimpse of it, through our own mechanisms, but not necessarily something that was meant for us to see. So, and that's going to be very hard to do, because why would they send out a big signal on their own planet that we would need to actually detect it ourselves? Why would they send out that signal? So we got to really look for very, very faint signals, which is why SETI, looking in the radio, is going to be really difficult to do for more distant objects.
This is outside the focus of your paper, but something we've talked about before with other guests is exactly this question, which is called METI, Messaging Extraterrestrial Intelligence. There are a group of people who are advocating that the human race start to broadcast to the world, or to the universe, to the galaxy at least, hey, we're here. And then there's another faction very strongly argues that would be the stupidest thing in the world, right? Because, using some evolutionary arguments, it's possible that if interstellar travel were ever possible, predator species may be more common than prey species. Yeah. And that to, yell out, we're here, until we know what's going on in the galaxy might be really dumb. Do you have an opinion on the METI controversy?
Yeah. So, of course, I have people who email me now daily saying that they do METI all the time. But of course, they think that they're being communicating with aliens now. You'd be amazed at some of the emails I get.
Yeah, probably via their dental fillings, right?
Yeah. I'm too afraid to ask in more detail. Some of these messages are very scary.
Yeah, exactly.
The communication with these other civilizations, I think, would be really hard to do, not just because of the distances. I think this goes to the Fermi paradox to some degree, if we get to that, is that these great distances make it really almost impossible to communicate. So if you have something 17,000 light years away, and we detect them, and we send off a signal to them when we detect them saying, hello, welcome to Earth or whatever, then it would take 17,000 years to get to them, and then if they reply, it would take 17,000 years to get back, right? Because the speed of light is constant. So that would take 34,000 years for us to receive an answer to our message, which is, that's a really long time. It's hard to imagine that. But at the same time, if the lifetime of those civilizations is only a few hundred years or even a few thousand years, then they would be long gone by the time our signal would reach them. So we really even could not communicate, even if they could detect our signal and could understand it and then send an answer back that we could understand. They would be long gone. So you have to have a combination of being close by, but also having a long lifetime of civilizations. Now, this whole idea about being scared of aliens and not wanting to transmit our information about our existence, I think is wrong. I think the reason for that, the reason it's wrong, is that if any kind of alien civilization is so highly technical that they could come to us and say, and potentially destroy us, which they probably could if they were able to transmit that amount of space, that civilization must be very advanced, much more advanced than ours. So they really have been around much longer than we have. I won't speculate how long, but let's say, thousands, millions of years longer than we've been developing our technology. So they have all kinds of technology, which is incredible, I'm sure. But at the same time, they've also had to manage to find a way to not destroy themselves. That is, they found a way where they haven't, done the equivalent of nuclear war or had, global warming destroy everybody or found a way to get people to wear masks when they have like a COVID type disaster going on like we do now, so that not everyone just dies away. So they've managed to figure that out, and that takes, I think, some sophistication. I think this is something that our own species still needs time to develop, is a sophisticated way of being able to live together, to survive for longer than a few hundred years with a high degree of technology. And this will be a challenge for humans in the coming centuries, is how do we manage this? We've already had to deal with it, of course, in the last 100 years, and it's only going to get worse with things like AI and who knows what else is coming up. So they've managed to do that. So I would like to think that they have, and maybe this is just me being crazily optimistic, is that they've managed a way to have a philosophy or a sort of the way they look at the universe, the world, and other living creatures, perhaps, is that, they're not there to be destroyed, but they're there to somehow live in some kind of, harmony or whatever, what have you, in terms of not just destroying things, but finding a way to be peaceful, to manage things better. So that's the way I like to think of it. Now, I could be wrong. So if an alien does come on and lands on Earth, I certainly wouldn't want to be the first person to come talk to it. But that's the way that I like to see it, and I think that the reason that they could survive so long, they must have a way of understanding that destruction is not a good way of keeping their civilization afloat. So that's kind of how I see that one.
And actually, that's may actually be an argument to urgently send out METI messages. I mean, it looks like we have lots of ways to kill ourselves. Maybe it's a lifeboat Mayday message. Hey, we're about to blow our planet up by nuclear weapons, or fry ourselves, or let loose nanobots that turn the planet into gray goo or something. If there's anybody else out there that managed to get past all these traps, please tell us how you did it. Yeah. Of course, per your calculation, it might be 17,000 years before we got the answer, in which case it may well be too late. In fact, actually, I had a thought when you were saying that there's another calculation you could do from your calculations. I would encourage your student to do this, which is that, let's say you set a parameter that you want two civilizations to be able to do at least 5 round trips, to be able to exchange their knowledge and touch points and translate each other's languages, etc. There is some L which will then create a probability map of how big does L have to be to have a 50% chance, say, of there being a civilization for which you could have 5 round trips. I know you can derive that from the numbers that you guys have put together. I'd encourage you guys to do that. It would be very, very interesting. Does L have to be 100,000 to be able to have a high enough density? What's the cool thing about your calculations is the longer L is, the higher the density is, right, and therefore the more round trips you can have, both because they're closer and because L is longer. They don't blow up while you're trying to have the round trips. That would be kind of a fun number to calculate. Yeah, it would. And it might actually tend to rule out a tight-knit. Well, I don't know what it would tell you. I'd love to do that. Another topic, before we'll get to the final one, which will be the Fermi paradox, is in addition to SETI classic search for radio and also just beginning laser, another branch of SETI that's getting more and more attention is the technosignatures branch of SETI, where instead of looking for emissions, we look at things that might be masking the emissions of stars. In fact, there's still one oddball candidate that has this odd variable signature of solar emissions, which is not known to meet up with any known type of star. And we have things conceptually like the Dyson shell, which is an advanced enough civilization builds a shell around its star to harvest all the energy, or a lesser version, the Dyson ring, which is a ring around its star, which occludes a fair amount of the solar energy. And so people are starting to look for technosignatures as well. And so far, they haven't found any, obviously, but there's at least one candidate, Tabitha's star, I think it's called. Is that what it's called? Yeah, I think that's it. Yeah. So anyway, your thoughts on technosignatures and what they might help or hurt or help refine some of these numbers in your revised equation?
Yeah, I really think that's the most likely way that we'll find a Chetty civilization throughout the galaxy, or even in other galaxies. Something that really hasn't been done too much is look for communicating intelligent life, so to speak, and other galaxies, because there's 2 trillion galaxies in our universe, and we're only really looking at one, and really only looking at a small volume of that one galaxy with traditional SETI. So I'm a big fan of looking for technosignatures. Now, people have done searches for Dyson spheres in our own galaxy using the infrared, looking for basically anything which is bright in the infrared, which is unexpected, and they haven't really found anything. There's really no good candidates for that throughout our galaxy. It doesn't mean there aren't any. It's just that what we can see so far, we haven't really seen anything. But that might just be our own galaxy. So if you have so many galaxies throughout the universe, and you have some probability of each galaxy having an advanced technology, then if you have enough galaxies, eventually you'll find a galaxy which has had a intelligent life in it for millions of years or so, hundreds of millions of years maybe. And over that period of time, you can really do a lot. I mean, you can really take over the galaxy, perhaps. If you look at the way that humans, of our technology has expanded throughout the last even just 100 years, just imagine what we could do if that rate of technology continued for centuries or thousands of years or millions of years. It would just be unimaginable, the things that we can do. So that, I think, is a really good approach to looking for SETI, is to try to find these kind of alien archaeology, archaeoastronomy type things throughout the universe, not just our own galaxy, but in other galaxies. Now, of course, the question is, how do you find such a thing? Okay, that's really the trick. What would these technology signatures look like, even on a small scale within a galaxy? Right? Would they just be Dyson spheres? Would they just be stars that are all sort of taken up by a sphere around them, where the light can't be seen, at least not in the optical, but in the only emits maybe in the infrared? Or would there be something else? And it's really hard to imagine what other things you could do. I mean, you could imagine maybe they move stars around. Maybe a galaxy has its shape changed by these communicating civilizations. Well, I shouldn't call them communicating, but these highly technical civilizations in other galaxies that can move stars around. They could have big regions of Dyson spheres. They can dim the whole galaxy so they can power up their civilization to do whatever they need to do. So I think that's really a good thing to look for. Now, there's very little work on that. So people have done a little bit looking in external galaxies for things, and I've actually done a project on this myself recently with some students, looking for galaxies which deviate from what we call scaling laws, which is where you have a very tight relationship between two quantities. If a galaxy falls off that relationship, the good question is, why does it do that? And one of the ways that might do it is if there's something altering the shape of the galaxy or that's light, and one of those things could be an intelligence. Now, it's very unlikely, and in fact, we didn't find anything either, but it's possible. And so people have done this a little bit, and this has been going around, I don't know, a long time now. 30 years is probably as long as people have been looking at this, but the papers on this are very few. So I mean, there's big gaps of like 5-10 years where no one does anything. But there have been papers in the literature for the last 30 years or so where people have looked for these kind of things in external galaxies. But very few people are working on that. And SETI, the mainstream SETI, is really looking for these radio signals and maybe the lasers, like you said, coming from nearby stars. But I really think that we should think more about looking for these kind of alien signatures in the technology overtaking part or all of a galaxy. I'd be really keen to see more people do that.
Yeah, it does annoy the hell out of me that if, SETI is, to my mind, the second most important scientific question. And unlike the first most important question, why is there something rather than nothing, we can actually do something about it. Why is the funding for SETI so small? And as we talked about early on in your introduction, why is it even considered dangerous for a career in astronomy or astrophysics to be a SETI person? It seems to me that if this is such a huge question, and we are actually at the place where we're getting real data, why shouldn't this be funded at hundreds of millions of dollars a year?
Right. That's a really good question, and I thought a lot about this. And if you look at the history of astronomy, there really are topics which are somewhat taboo and discouraged from people looking at. Even astrophysics itself 150 years ago was considered to be sort of a rogue thing, and it wasn't considered to be mainstream astronomy. Astronomy back then was looking at star positions and stuff like that. And people like Auguste Comte, the philosopher, the French philosopher, said in the beginning of the mid 19th century that we'll never know what stars are made of, these kind of things. But then people got spectrographs, started looking at stars, and found out, yeah, we know, only a few years after he said that, people knew what stars were made of. And then you have a great example, which I think is the closest example to SETI, is cosmology. So for a very long time, people who thought about the idea of where did the universe come from, how did it start, how old is it, all this stuff, were thought to be, this is religion. This is not something that really a serious scientist should look at. But of course, now cosmology is mainstream astronomy. It's mainstream astrophysics. And it in some ways dominates the field, dominates the funding. So SETI is similar to that. And you're absolutely right that it's one of the big questions. It's really up there with top 2 or 3 questions you could possibly ask in all of science. So why is it not really well respected? I think it's simply because there's really no data, and that's sort of the same thing that you had with the problem with cosmology. So certainly whenever we do detect sort of life, and I think that will happen in the next decade or so, I think we will detect some kind of life on other planets, evidence for it. But that life will be very simple. It could be analogous to plants or something like that. And it'll be found just by looking at chemical elements in the atmospheres of planets, which is something that we can do now quite easily, although not to the ability to find evidence for life. But there are many new telescopes coming online, like James Webb Space Telescope, and these big new telescopes that'll be 30 meters in diameter on the ground that can do these spectroscopic studies, that can find these elements and molecules in the atmospheres of planets, which can tell us that perhaps, or definitely, there's something going on, which is probably some form of life. So I think that will happen, and that I think will help a lot. And I think when we discover that, there'll be a lot more enthusiasm for looking for intelligent life, which will be much harder to find.
Glad you mentioned that. I was going to do that, which is that we're right on the verge of either detecting or not exolife by looking at the spectroscopy of atmospheres of exoplanets. And it's possible it might be a dry hole. I mean, it could be that we'll look at several hundred habitable zone planet atmospheres and find no life signature, which would start to fill in one of the terms in the equation, in the original Drake equation at least, which you guys chose to not get into. Which I think is a perfect transition to the not to the Drake equation, to the Fermi paradox, right? As people listen to the show know, anyone with a scientific background, I always ask them about their view of the Fermi paradox. And to restate the Fermi paradox, it goes back to Los Alamos, at least this is the story that I've heard, where a bunch of young scientists sitting at the lunch table were speculating, there's got to be 100,000 smart, intelligent civilizations in the galaxy, yada, yada. And Enrico Fermi, the famous physicist, came up to him and said, where are they? And if they're there, where are they? And that's been this question, the Fermi paradox. How many are there? And if there really are some, why haven't we seen any sign of them? And there's arguments on both sides. One, essentially the Fermi paradox literature tends to divide the analysis up into 2 classes. One, that there aren't any, and 2, that they're there, but for various reasons we can't see them, or they don't want to see us and are actively avoiding us. In fact, there's a great book called If the Universe is Teeming with Aliens, Where is Everybody? By Stephen Webb, which goes through 75 different solutions to the Fermi paradox and allocates them to the different buckets, and there is nobody there. Some of those arguments are things like, life is exceedingly difficult, or maybe not life, maybe simple life is real simple, but what happened right before the Cambrian explosion 540 million years ago, where the template that was laid down for all interesting multicellular life of our sort and every other interesting animal we know, maybe that was a really weird long shot, or maybe the development of chloroplasts was an exceedingly long shot. I think we've learned now that's happened more than once. So that's one side. And then there's a bunch of others, on the other side, which is everybody gets eaten by their AIs within 100 years, right? or they just decide, the dark forest theory, got to be quiet, there's bad guys out there. So I'd love to know your thoughts. I mean, if you've been working in this space, you have to have speculated about the Fermi paradox. If you had to put your flag on the ground, why haven't we detected anybody?
Yeah, it's a great question, right? And yeah, indeed, I have thought a lot about this. So my solution to the Fermi paradox is simply just the fact of distances and rarity. So if these kind of communicating extraterrestrials are rare, then they're going to be far away. And if they're far away, they're going to be really difficult to detect. And I would say a third thing is perhaps the lifetime of civilizations is not as long as we would like to think they are, that they're actually not very long. So if you have those three things, and if you have those three, then it's easy to solve the Fermi paradox. It's simply that there are maybe a couple of civilizations in our galaxy, but they're really primitive, like us, or close to us, and they're so far away that we're not able to detect them, and they're not able to detect us. Now, you have to remember, if someone's looking at us, at Earth, they would never see that we have a technical civilization unless they're about 100 light years away from us or closer. If they're further than that, we still look like a normal planet, right? We don't even barely have lights happening. Lights are a bit older than 100 years. But anyway, you get the idea, is that our bubble of intelligence that's projecting out into space is only about 100 light years in radius, which is not very big for the size of the galaxy. And there's very unlikely to be intelligent life within 100 light years of us. It's just very unlikely. Those stars almost certainly don't have it, or else we definitely would have noticed something by now, I would think. So by the fact that it's so rare and so far away, it's unlikely to be seen. And then if you have a short lifetime, then also unlikely to be seen, simply because they don't last long enough to develop a highly technical civilization that could reproduce itself on other stars, or make robots that can reproduce themselves and don't even need the biological alien anymore, but can survive for perhaps tens of millions of years just by self-replication and going throughout the galaxy, and that eventually would come to us, but we haven't seen that. So that's another sign that I think that this lifetime of these civilizations isn't very long, but it could be combined with the rarity of them as well, which is another reason why I think looking at external galaxies is another way of trying to find these things.
Okay, that's interesting. So essentially, it's a density is low and the average lifetime is short. You run the math, and it's not surprising at all that we haven't detected anybody. I think you were saying in your paper that it's based on some reasonable set of assumptions, even including your rather optimistic assumption that life is easy.
That's right.
It might well take thousands of years to detect a civilization via the current level of effort in the SETI space, and obviously we've only been doing it for 50 or 60 years. So Okay, very good. Well, this has been a wonderful conversation on one of my very favorite topics, and I really want to thank you for being here.
Thank you very much for the invitation. I really enjoyed it.
All righty, thank you very much. Production services and audio editing by Jared Janes Consulting. Music by Tom Muller at modernspacemusic.com.